Hello and welcome to session number 5. In this session we're going to try to figure out how to change the properties of a semiconductor material. Specifically, how many mobile electrons are in the conduction band. But before we do that, we're going to listen to a really magnificent, one of the most beloved arias in all of the classical repertoire, O Suave Funcella, O Dear Maiden, in the moonlight so lovely, in you I see the answer to all of my prayers. And then the explosion, love all over me. O Suave Funcella from Puccini's La Bohème, and I'll see you back in about 4 minutes.
E al ritorno dammi il braccio mi appiccina obbedisco Signor
these are the topics that we'll be covering today. First, a review, light energy and wavelength, and then we're going to talk a little bit about resistance and Ohm's law, partially a review and partially new materials. And then we get into the formal part of the session, and the formal part of the course really. We're going to be looking at how do we change the number of mobile carriers in a semiconductor material. It will mostly be descriptive. However, there will be at the very end a little bit of mathematics when we talk about an intuitive derivation of the Fermi function, and we'll end with a short video clip, the finale to the really incredibly wonderful movie Light Between Oceans. So let's get started. Review of light energy and transparency. Light, also known as photons, possesses energy, even though it does not have mass. If it didn't have energy, then there would be no solar cells and there would be no lasers. The energy of a photon depends on the frequency, and the frequency is inversely proportional to the wavelength. And last time we developed this relatively simple formula. The energy of a photon is equal to 1.24, just a constant, comes from the multiplication of Planck's constant and the velocity of light, divided by the wavelength. The energy is in electron volts, the wavelength is in microns. So for the infrared, because it has a low energy, because the wavelength is large. Red has an energy of about 2.1 electron volts. Blue has a smaller wavelength and therefore a higher energy of about 3 electron volts. And ultraviolet has the highest energy yet because it has a very small wavelength. And if we would continue, we'd get into gamma rays and all kinds of horrible things which are very dangerous. Now let's look at transparency by superimposing on the energy of the photon the energy band diagram, specifically showing the energy gap. The energy gap of silicon is about 1.1 eV, and on the right side I have aluminum oxide, crystal aluminum oxide, also known as sapphire, which has a band gap of about 9 electron volts. And both I have red impinging on both materials. Well, on the silicon, the energy of the red photon is higher than the band gap, so the energy of the photon, or the photon I should say, is able to kick an electron out of the valence band and push it right up into the conduction band. So the photon is absorbed by the silicon, and therefore it doesn't get through. It's stopped. Therefore the silicon is not transparent. It appears as grayish in color. That's also true for gallium arsenide, which has a band gap of about 1.43, and a number of other important semiconductor materials. However, for sapphire, you can see the energy is very low. This is not drawn to scale. The energy is very low of the photon compared to the band gap. So what happens is it just goes right on through. Do not stop. Do not collect $200. Does not have enough energy to kick an electron out of the valence band into the conduction band, and therefore it is transparent. Now here's a question before we get started on the formal part of our material. How do we control the resistance of a semiconductor material? Well, let's remember, I hope you recall, the current density of a semiconductor material, if they're a mobile charge, and a voltage or an electric force. The current density in amps per square centimeter is equal to the number of mobile carriers, and this is the important one right here, times the electric charge, 1.6 times 10 to the minus 19th coulombs, multiplied by the velocity, not the acceleration, because we are ohmic, we are not Newtonian. And you recall, I hope, that the velocity of the charges is equal to the mobility multiplied by the electric force, and the electric force is equal to the voltage divided by the length of the sample. Therefore, we continue here, and we say that the current density is equal to the current, because I want Ohm's law, divided by the cross-sectional area, the width times the thickness, and I rearrange things by isolating the voltage and bringing all the other stuff on the other side, and I get that the voltage is equal to some constant multiplied by the current. All of this constant is the resistance. Now let's put in some numbers. First, assume we're dealing with a cubic material. So the first term we're going to say is just 1. Omega t divided by L is purely structural, and we're going to assume that's about 1. We don't have to deal with it anymore, which is nice. N, for now, let's that be the intrinsic number of electrons at room temperature. We will calculate this in future sessions, but I can tell you that it's about 10 to the 10th electron hole pairs per cubic centimeter. So that is N. The electric charge, of course, is 1.6 × 10⁻⁹ and the mobility, well, we have to guess that for now. There are ways to at least estimate it. We're going to assume the mobility is about 1,000. It's a bit on the high side, but that's close enough. So we put all those numbers in. This is 1 divided by 10 to the 10th, 1.6 × 10⁻⁹, 1,000, and we get about 600,000 ohms. That is a big number. That could not make a useful device. However, suppose we're able to increase this N from 10 to the 10th to 10 to the 16th. That's 6 orders of magnitude. You can say, how do we do that? Well, that's our task. Then, if we're able to do that, then we have about 0.6 ohms for our sample, and that is a very useful device indeed. And our task is to see how we accomplish that. So first, let's take a look at a salt water analogy. And this is going to be a little bit obtuse, perhaps, and it's going to seemingly to be a little bit difficult to understand, but let's hang in there and see if we can get this. So I would like you to consider 2 cups of water, clear glasses of water, cup 1 and cup 2. Cup 1, I don't see which one is which. Okay, it doesn't matter. Let's just say cup 1, this contains pure water. Cup 2 contains water which has in it enough salt water so that it is completely saturated. And if I put in any more salt, no matter how much I stir it up, it just doesn't have the ability to hold any more salt. So cup 1 is pure water, cup 2 is a saturated water solution. And I ask the following question: how do I tell them apart? And this is the question that I've asked every time I've taught this material. Generally, the first session, the first couple sessions, I have a relatively big audience, and I'm trying to elicit the following response. I'm trying to elicit the response, that's easy. All I do is dip my finger in and I taste it, or I dip a teaspoon in and I taste it. Salt water tastes different than pure water. Well, that's a good answer, but suppose that I tell you that in addition to the salt that I put into cup 2, I also put enough poison to kill a horse. Then I don't think that is a particularly good solution. And which leads me to the first joke of the day. Oh boy, this is, actually I think you might enjoy this one. This is the story of Lady Astor and Lord Winston Churchill. They apparently detested one another. So as the story goes, they were having a violent argument, and Lady Astor gets so upset, she lashes out at Churchill, and she says, "Mr. Churchill, if you were my husband, I would put poison in your tea." To which Churchill famously responds, "Lady Astor, if I were your husband, I would drink it." Okay, so that test, the test of tasting, doesn't work. Is there another test? And here I get a relatively confused expressions on everybody. There sometimes 50 or 60 students in the class, and I get no response at all. I'm going to claim that one way to tell the pure water from the salt water is to take both cups and put them in the freezer and lower the temperature to close to freezing. What will happen, I claim, and you can do the experiment yourself, is that the cup which has the salt water, the salt will come out of solution. And that's a big deal. There's something about temperature which makes the ability of water to dissolve salt less if the water is cold and more if the water is hot. So if I take it back to room temperature, I can dissolve the water, and if I bring it up in temperature close to boiling, I can even put more water. So temperature is a big deal in dissolving water. And here we have a energy band diagram for salt water. Well, there is no such thing as an energy band diagram for salt water, but that's okay. We're going to make one up. So I have pure water down here. I have dissolved salt saturated up here, and I'm going to claim that as the temperature goes up, it is easier to dissolve the salt in the water. There is some what we call state of the water, and that state of the water goes down towards pure water as the temperature goes up, and it goes up towards saturated salt solution as the temperature goes down. Now there's another part here, and that is how much salt is dissolved in the salt water. Salt water cannot dissolve salt without any bound. You can't keep putting salt in water, just like you can't keep putting sugar into your coffee. You put too much sugar and the coffee just refuses to dissolve anymore. Try to put too much salt, no matter what the temperature, into water, there comes a point where the water simply cannot dissolve any more salt. So the state of the water, also known as the chemical potential, goes up as we increase the amount of dissolved salt. So there's two parameters right now. Decrease the temperature or increase the amount of dissolved salt. This magic number, which we're going to call chemical potential, rises. Increase the temperature or takes salt out of solution, and this chemical potential decreases. And there's one more factor, and that is environment counts. The effective environment is also important. And what is all that about? Well, what I'm claiming here is that you can't dissolve salt in canola oil. Now, I've never tried this myself because I try to stay out of the kitchen as much as possible. However, the general rule is that polar dissolves polar, nonpolar dissolves nonpolar. Canola oil is nonpolar, water is polar, salt is polar, salt dissolves in water. Salt should not, although I don't have empirical data to prove that, I'm claiming that salt should not dissolve in canola oil. Environment matters. And we'll see the exact analogy, a very similar analogy, I should say, not exact, when we talk about the doping of a semiconductor material. So now let's put all of this stuff together and say there is a driving force to take the salt, which sits at a state in water close to the dissolved saturated solution, and is this driving force the length of this arrow which drives the amount of salt which is able to be dissolved. The bigger the arrow, the bigger the driving force, the more salt we can dissolve. If the salt energy solution goes down, for example, if this dotted line was down here, the driving force would be much lower, and the ability to dissolve the salt would be much, much lower. That's canola oil. In the semiconductor world, these are called deep or trap states or deep states, and we'll talk about that a little bit later on. Okay, some observations. Only the salt and dissolved salt energy levels are occupied. There's no salt here. The occupation of the salt is either here or here. If it dissolves, it jumps up from this level to this level. That's the first observation. For every dissolved salt molecule, one sodium and one chlorine ion are formed. The number of sodium ions precisely equals the number of chlorine ions. And that makes sense, because you just break them up. We have two mobile ions. Both sodium and chlorine are mobile. They conduct electricity. It is not particularly well known, but it is true that pure water, and I mean pure, I mean no dissolved salts at all, does not conduct electricity. And in the semiconductor laboratory or fabrication plant, we have to be very, very careful to make sure our water is pure and does not conduct electricity. I believe it's about 81 megohms, I think, for the conductivity or resistivity of pure water, extremely high. Okay, all lines here are horizontal, and we have not yet identified the horizontal axis. However, we have identified the vertical axis, and it is energy. Okay, now if we combine a salty solution where the chemical potential is very high, close to the saturated salt solution, with a chemical or a system or a cup, if you will, which has very little salt, the chemical potential is close to that of pure water. What happens? Well, when you can put salt water into pure water, the pure water becomes salty, and the salt water becomes less salty. And that's exactly what happens when we put two semiconductor materials together. And here is a table which illustrates the difference, or the similarities, I should say, between dissolving salt water in solution and doping electrons with donor atoms. So this table describes the difference between dissolved salt water and doped semiconductor materials. First, let's concentrate only on the left side, because that's what we've been talking about, and then we'll make the analogy to the right side. We're dissolving salt, so salt is one of the components. Pure water, we start with pure water, we dissolve salt. How do we do that? We just pour salt into the water. Well, that's not all we have to do, however. In order to get that salt to dissolve, good idea to stir it up. Take a spoon and stir it up vigorously, and that ensures that the salt will dissolve in the water if the temperature is high enough and if we don't have too much salt already dissolved. there is something called a salt level, which is close to the saturated salt level, and that depends on the environment. If it's water, it's very different than canola oil. Salt level in water is close to the saturated salt solution. The salt level for canola oil will be very close to pure water. It is hard to dissolve salt in canola oil, and it is much easier in pure water. The dissolved saturation level is this level at the top here. This is the pure water. This is the state which goes up and down, and the state of the salt is very close to the dissolved salt level if we're in pure water. So just to repeat that, now that's shown more explicitly here, and there is a driving force which forces the salt to be dissolved. The bigger that arrow is, the easier it is to dissolve the salt. And you can see as we dissolve more and more and more and more salt, this level goes up and up and up and up, and eventually the driving force goes to zero, and it becomes very difficult indeed to dissolve salt. The chemical potential moves. It moves up and down as a function of the amount of dissolved salt and the temperature. The fraction of dissolved salt is simply how much salt is dissolved in relationship to the total amount of salt that's in the water. In fact, you can have a situation where you have a lot of salt and it is super saturated, so you have some salt which is dissolved and some salt which is not dissolved. Now let's go over here. The salt is the donor atoms, specifically the most important one is phosphorus. So instead of salt, we're dumping or doping phosphorus into a silicon lattice. Pure water is intrinsic semiconductor. Pure semiconductor. Pure silicon. Not perfect, but pure. We pour water into we pour salt into the water. The analogy is that we ion implant donor atoms into the semiconductor lattice. Stirring the salt has its analogy in activating the donor atoms. We do that by heating the wafer to about, I think it's about 800 or 900 degrees centigrade, and that's enough to shake things up. And so the phosphorus atoms, which were kind of randomly positioned in the silicon, now work their way in and displace some silicon atoms, and when they do that, they're much more able to donate their electrons. The salt level has an analogy in donor electrons, donor energy states, and we'll see that on the energy band diagram for silicon in just a little bit. The dissolved saturated salt level, that's that upper band, is the conduction band edge in the energy band diagram. The fraction of dissolved salt is the percentage of phosphorus which is ionized, the percentage of phosphorus atoms which give up an electron to the conduction band, leaving behind a phosphorus positively or negatively charged. Well, the phosphorus atom was neutral. If it gives up an electron, what do you think it becomes, positive or negative? So when you think about it, I hope you'll come to the conclusion that it becomes positive. Gives up an electron, it was zero, it becomes a positive ion. The chemical potential in the silicon world is called the Fermi level. Okay, so let's look at the energy band diagram with all of that stuff for donor atoms in silicon. We have the Fermi level, which goes up and down. As we increase the temperature, it goes down. As we increase the amount of phosphorus atoms that are able to donate an electron, the Fermi level goes up. If the Fermi level rises up to here, in this region right here, then that driving force basically goes away, and any phosphorus atom that we implant into the silicon lattice will have a very hard time giving up its electron. So if you compare this diagram with the salt, you'll find that they are essentially, I was going to say identical, they're not identical, but the analogy I think is very clear. The salt is closer to our hearts because we can actually do the experiment. Unless you, and yes, you have $2 or $3 million to buy an ion implant, right? This experiment is hard to do. Okay, there is another really big difference. You can read this. This is right out of the text, so I'm not going to belabor this too much. However, the difference between doped semiconductors, or semiconductors which have phosphorus implanted into them and donate an electron, and the salt solution. What happens in the salt solution? When the salt is dissolved, it breaks up into two species, a positive sodium and a negative chlorine, and they are both mobile. They can both conduct electricity. That's not true here. What happens here is that the phosphorus atom donates an electron. The electron goes up into the conduction band, leaving behind the atom which worked its way into, I should say the ion, which worked its way into the silicon lattice and is immobile. So we have essentially part of the silicon lattice which has ions, which actually is positively charged. I should just mention here, I put this on the diagram, the amount of salt which would define a saturated salt solution has an analog in the silicon world of the amount of electrons which the conduction band is able to support without revolting, and that's about 10 to the 19th electrons per cubic centimeter. And that indeed is will give an extremely small resistance. 10 to the 16th gave about a half ohm. 3 orders of magnitude less gives essentially almost a short circuit. So that's a good thing. If we're able to produce that many electrons, we call that degenerate doping, and we'll have some more to say about that a little bit later on. Okay, if you thought that was confusing, I should take a deep breath, because now we're going to talk about the inverse of phosphorus, which is P-type. All of this referred to N-type. And in N-type, where is it? Must be here. Oh, here it is. N-type, the Fermi level is above the intrinsic level, the pure silicon level, and the Fermi level rises as we implant more and more phosphorus into the silicon lattice. Well, I'd like to think about the P-type. One way to think about it is stand on your head and look what happens. Everything we said here is the exact opposite. And let's just take a look. You can read the observations. This is from the text, so I won't belabor this too much. And I'll go right to the energy band diagram for P-type. Don't worry if you don't catch all of it. We're going to look at this from a number of different perspectives, so it hopefully will become clearer as the sessions wear on. Notice that the Fermi level is below the intrinsic or pure level. The ionization force, driving force, the magnitude depends on where the Fermi level is. As we implant more and more boron or p-type, the Fermi level, instead of rising, again I mentioned stand on your head, and the Fermi level falls. So the Fermi level goes down as we increase the number of boron atoms, and therefore it becomes harder and harder for the silicon lattice to accept an electron from the boron. So I won't say too much more about that. You can read about it in the text, and I know it's confusing. It was certainly confusing for me when I first learned this, and we're going to leave it at that right now, and we're going to attack it again next time from a slightly different angle. But I just like to take a look at the total diagram right here. We have the conduction band, the valence band, the intrinsic level, the Fermi level. So I'll ask a question, is this N-type or P-type? And the key is, where is the Fermi level with respect to the intrinsic level? If the Fermi level is above intrinsic, it must be N-type. So this material is N-type, and it has a fairly large driving force. So when we put in the next phosphorus atom, the probability is very high that it will give up an electron into the conduction band. Now, how about if we put in a boron atom? Well, the driving force for boron is the difference between the Fermi level and the acceptor level, way down here. That is a huge driving force. So we would have an arrow from this level to this level, almost twice as big as the driving force for phosphorus. So if the phosphorus is going to be ionized, you better believe that the boron will certainly be ionized. So please read that in the text in chapter 3, and that is indicated here. The ionization driving force for an acceptor atom like boron is much bigger than the driving force for a donor atom like phosphorus. Okay, so this is I probably should have put this in the last session, but this is a table of semiconductor materials, their lattice constant, and the band gap. And you'll notice for the pure materials, as the lattice constant goes up, the band gap goes down. Okay, so finally, actually I'm going to skip this for now, and because it's really quite a difficult session. I understand that. I get it. I do get it. So we'll start here, session 6, next time, and I'll then skip over to a wonderful video clip. This is a movie, Light Between Oceans. If you haven't seen it, I urge you to see it as soon as possible. It is a magnificent movie. And the book, also called Light Between Oceans by M.L. Stedman. Read the book and see the movie. It is powerful and life-changing. And I'm just going to play the finale here. It's about 5 minutes long. You might, and I do this routinely with classes that I teach. I play a finale and I say, see if you can come up with the theme of the movie only from the finale. So looking at the finale, see if you can get some idea perhaps if you haven't seen the movie, before you see the movie, what the movie is about. And we'll see you next time.
Do you think God will forgive me?
He forgave you a long time ago.
It's about time you did.